Welcome to lecture 41 on risk management and insurance. In this course, we have seen that economists use utility function to model the behavior of people in economic settings, so in markets. So those utility functions, they capture the tastes of people. For example, in chapter 2, in this course, we used a constant absolute risk aversion utility function and the constant relative risk aversion utility function to explain the willingness of people to pay for insurance. So this explained the demand for insurance. Now, in this chapter here on stochastic dominance, I will assume that actually we do not know the utility function. Economists make a great effort actually to estimate those utility functions. So that's done by econometricians. So that's a big field in economics. They try to estimate what are the tastes of people. Okay, what is really the shape of those utility functions? What are the parameters of those utility functions? But let's assume now that we don't know the utility function and we cannot estimate it. Then we still can actually say something meaningful on the demand for insurance. And that's actually done here in this, on stochastic dominance. So stochastic dominance applies to a situation where we do not know the utility functions. But you should be aware, okay, that there is a big effort naturally in economics really to estimate those utility functions. Now, first order stochastic dominance, you simply assume in first order stochastic dominance that the utility function is upward sloping. And that's the only assumption that you make. You don't say how strongly it's upward sloping. Okay, you don't say anything on the curvature. You just assume that people prefer more to less. So you have here a positive first derivative of the utility function. People prefer more to less. Actually weakly. So we also can have here an equality sign. But basically you can say people prefer more to less. The utility function is upward sloping. We don't say anything on the curvature. So people may be risk averse, but they also may be risk neutral or risk loving. So we make here a very weak assumption on the utility function, but we don't know the utility functions. The only thing we know that people prefer more to less. So we have here a first derivative of the utility function is positive or equal 0. They weakly prefer more to less. So that's quite a weak assumption, so that probably applies to most people. That's the assumption behind first order stochastic dominance. So let's now look at two risky prospects. Okay, and they are described by the following cumulative distribution functions, f and g. And we assume that the domain, then actually of f and g, they are over a closed interval, so it does not go up and down, up to plus infinity and negative infinity. Okay, we cut it off. Okay, so we just look it up in an interval from a to b. That makes it a bit easier, the analysis. So here we have the definition of first order stochastic dominance. The distribution f, first order dominates g if and only if the decision maker weakly prefers f to g under every weakly increasing utility function. So the utility function is increasing, that's assumption, but that's really the only assumption here. We are not interested in curvature. And the distribution f is preferred by the decision maker to g, okay, if the expected utility of f exceeds or is equal to the expected utility provided by the distribution G. Now the expected utility I'm calculating here, you see, you have each utility of X, you multiply with its probability, and then you sum it up over the entire interval A to B. So I do it here with continuous variables. So the integral just again means a summation sign. And how you calculate the mathematical expectation, you know this, it's usually written down like that. Okay, you have the possible outcomes. Okay, Ux, and then you multiply each one with its probability, and you sum this up, and you get the expected utility. And then for fx dx, you can actually write df. In the Zweifelbook and in some books, they prefer to write df for fx dx. But naturally here, if you have the change in x times the rate of change here, okay, this gives you the change in the value of the distribution function, of the cumulative distribution function. Just think of the triangle. Okay, you have the x times here the slope, okay, the rate of change. So this gives you just the df. So I use here, you know that from first year statistics classes, I use here, okay, just a notation for an expected value. And that's also here just a notation for the expected value. So I have here the expected utility of the f function. Now, if that expected utility is bigger or equals than the expected utility of the prospect G, then then f dominates G. Now, I will draw you a graph in a moment, and then this will become again more clear. Now, the second definition is actually equivalent to the first definition. So for f first order stochastically dominates G if and only if actually fx is smaller equal gx for all x over the domain of the function. This means that the f must lie, the function value f must lie below G, f must lie below G in its entire domain. So over the entire domain, okay, from A to B. The x's can go from A to B. So f and G are not allowed to intersect. Now, those two definitions are actually equivalent. For the proof that those two definitions are equivalent, you can actually look this up again, okay, in one of those open course software, open course courses at MIT. Okay, that's where I have it from. Anyway, so we said here, f first order dominates G if the f value is always smaller than the G value when you plot that. And that's what I have here. So I have here now the interval from A to B. That's the x variable, that's a random variable here. And then I have here the cumulative distribution function f. I have the cumulative distribution function G. And the f value must be less than G, okay, for all the x's here between A and B. So the f value must be less than the G value for all the x's between A and B. Now, why does this make sense? I have it actually here in the text. So here, for every probability, remember here we have the probabilities. This goes from 0 up to 1. It's a cumulative distribution function here. We have here cumulative distribution functions. So it shows a probability that a value is less or equal to a critical value. So we have here the probabilities. And so you take here for any probability, for any outcome, here actually F is bigger than G. So for every level of probability, F, okay, so X here, this X value here is bigger than the X value of the G function. So the wealth, that X just stands for the wealth, okay, so a decision maker who prefers more to less, will prefer F to G. Okay, maybe again. So here we have those two different type of prospects you're looking up. See, we started here. We look at two risky prospects that are directly described by those cumulative distribution functions. Naturally, we could also show the PDFs, the probability density functions, but I work now here with the CDF. Those two prospects, which prospect does the decision maker prefer? And we do not know the utility function. The only thing we know is that the decision maker prefers more to less. The utility function is upward sloping, but that's really all we know. So we have here the prospect F. Okay, that's maybe that's the prospect G. So I do it here a bit theoretical, but you can maybe those outcomes are maybe again that just from an investment. Maybe one investment gives you this outcome, the other investment gives you those outcomes. They are shown here by those cumulative distribution functions. And then, okay, so F is the preferred one, because if for every probability here, here's the X value is bigger than here. And the X is, those are just the wealth. So X is, this stands here for the wealth. For whatever you take here as a probability, F gives you higher wealth than X. And so a person who prefers more to less will actually now prefer this prospect F. You can also say low wealth is more likely for G. You see here it goes up faster, so CDF. So actually we have here more higher probabilities. So those lower values here of wealth are more likely for the G distribution. And so if you prefer more to less, then you don't like that. That's first order stochastic dominance. Okay, so it has, G has more mass in the lower tail, G is not so good, okay? It's likely that you are here, okay, where wealth is low. As I said, the two definitions that we did are equivalent. You can look this up here. But so it's easy. If we have two risky prospects, maybe two types of investments, and that's the wealth here, and that's actually the CDFs. That shows you the distribution, of those two prospects. Then the person will prefer the F. To the G, because this gives you the higher wealth. So it's easy if those two curves do not intersect. It's quite obvious, it's common sense that you prefer the F. But if they intersect, then it's getting more difficult. So you cannot use this if the two curves intersect. So ideal now is this situation where the two prospects have actually intersecting CDFs. Okay, again, it's a bit a topic that requires some intuition. The math is not difficult, but just what's going on here, one has to think a bit about it. Okay, really, it requires a bit, a bit of thought. Maybe so you discuss it with a colleague. Now, if the if the two curves intersect, then you really cannot say, okay, then first order stochastic dominance does not say which one you prefer. And you have to move to second order stochastic dominance. And you just make stronger assumptions. So in second order stochastic dominance, you still assume that the utility curve is upward sloping, but now let's also assume that it is concave. So we have risk aversion. So that's all we know. We don't know how strong the risk aversion is. We don't know, okay, whether it's actually constant relative risk aversion or constant absolute risk aversion or another type of risk aversion. There are also other functions around. Okay, so but we know, okay, the curve, let's assume the curve is upward sloping and people are risk averse. That's probably true for 99% of people. There may be some risk neutral people around, or maybe some risk lovers, as we discussed in chapter 2, but the vast majority of people naturally will be risk averse. And so again, this assumption seems to be quite a natural assumption. People prefer more to less, and the vast majority of people can be assumed to be risk averse. And then actually we can also distinguish between risky prospects where the CDFs are intersecting. We must make stronger assumptions. We must assume risk aversion, but then we can also deal with this situation. Now we have three definitions. We have three definitions for second order stochastic dominance, and they're all again equivalent. Again, you can actually look this up, okay, in this course at MIT. So the definition 1 is again based on the expected utility. Again, the expected utility must be bigger, okay, than the expected utility of G, then F is preferred. So we prefer F to G under every increasing concave utility function. So what's new here is just the utility function is concave. We have a risk aversion. Let's go back to first order. You see here is first order, it's exactly the same sentence, but I don't have the concave here. Here for first order, I only assume that the utility function is upward sloping. And then we look here at the expected utility. Now with second order, again, I assume that the utility function is upward sloping, and on top of it, I assume that it's concave, that we have risk aversion. And then again, here we have second order stochastic dominance if the expected utility, okay, is bigger, okay, if we have this type of utility function. So again, here we have the expected values written down. And if you like, again, you can break up this df. You can write it down as I have it here in the footnote. You see for the df, again, you can write down fx. You can write here the density times dx. This gives you the df. And the same thing, okay, for the g. That's just how you write down expected values in statistics when you use integrals. Integrals are just sums. We said you sum up, okay, each outcome, utility outcome, you multiply by its probability basically, okay, and you sum it up, okay, and then you have the expected value. Okay, this was the first definition. Now, this first definition of second order stochastic dominant is equivalent to this second definition. And look it up maybe then on this website of MIT. F second order stochastically dominates G if and only if G is mean preserving. Is a mean preserving spread of F. So we should know what is a mean preserving spread. It's something that actually plays a bit of a role also in this literature. Now, in a mean preserving spread, a random term epsilon is added to the random variable x. So I have here a random variable x, and I add here another random term with an expected value of 0. And then I'm getting a new random variable y. So I start with a random variable x, I add another one with an expected value 0, and I'm getting a new random variable I. Now, a risk-averse decision maker prefers x to y, because y will have a bigger spread than x. That's the same mean. You see, it's mean preserving. By assumption here, the mean of epsilon is 0. But epsilon will actually increase the spread here, will increase the standard deviation. So adding the random term epsilon to x increases the risk. It increases the standard deviation without increasing the expected value, the mean. So the y variable has a bigger standard deviation, it has a bigger risk than the x random variable, because we have here added another random variable to it. With a mean of 0. That's a mean preserving spread. You add up two random variables x, you add another one epsilon with 0 mean, you get a new random variable. So this new random variable has actually the same expected value, because this one has 0 mean, but it will have a bigger dispersion. I assume here that the covariance between x and epsilon is actually 0. So the epsilon movements do not counteract the x movements. Okay, so that's a mean preserving spread. So f second order stochastically dominates G if and only G is a mean preserving spread of f. So G has a bigger dispersion but the same mean. And this definition is actually equivalent to that definition here. Okay, that the expected value of G is smaller than the expected value of f. That's why we prefer f here. Now here G has a bigger dispersion. That's why we prefer f, and they both have the same mean. And then the third definition. Okay, for this one I will present you a graph on the next page. So you have in the interval from A to B, over that interval, that's a domain of the CDF, that's on the lower axis, it goes from A to B. Now, if you do the integration under the F now here, then, okay, if you have less here than here, okay, so the error under the cumulative distribution F must be less than the error of G, okay. Then F, again, second order stochastically dominates. So F second order stochastically dominates G, if and only if for every t in the interval, okay, this integral here is less than that integral. So here you think of errors. I have it here. So here again you have the x variable, that would be the wealth. The two cumulative distribution functions, they show us just the possible outcomes. We go from A to B, okay, so actually cut it off, okay, we have just this closed interval here, okay, we don't go up here to infinity and to minus infinity in distributions. It makes it a bit easier. And now, for every t inside this interval AB, the error under F, okay, is less than the error under G. The error under F is less than the error under G, then F actually second order stochastically dominates G. I will explain a bit further. So this area here up to point T under the curve is less than the area under the other curve G here. Then F is preferred. That's again the idea. You see, if you take here the probability, actually a given probability, then the F gives you a bigger X value. You see, so actually the wealth will be higher. That's what we had before. But here we have trouble. Okay, they start to intersect. So, but if it's true that even after this intersection here, still we have the bigger error under F than under G, then F is still preferred. And that's the case, okay, when this area here in between, now I'm looking now at this area between the two curves. If that area A is bigger than that area B, then actually, okay, then the areas, okay, you go under the curves here, okay, under the curve F will be bigger than the curve G, even here at the points after the intersections, okay, when you go beyond the intersection here. Okay, so that's not so easy to see. So you really have to think. I don't blame you. Okay, if you have to think a bit about that one. You see here up to the intersection, it looks like here. Up to the intersection, F is always less than G. So actually, F gives me for a given probability, F gives me the higher X value. It gives me the higher wealth. It gives me the higher wealth. So up to the intersection, okay, so F gives me the higher wealth. It's preferred. Now after the intersection, we have a problem. Okay, but you see, we still have actually here, F is much bigger than the area under F up to the intersection is now here much bigger than X. Now here, the area is still bigger, it's still big. Now this we lose now, but on net, we gained this before. And so actually, if this area here between the curve is smaller than that area here, okay, then actually the F remains the preferred distribution, even if they intersect here. So the F here, you see what you have under the F here must be less, and it's actually less. If you look under the curve, this F is less than what you look here, and it will remain less, okay, if this area B here is not too big. Okay, the three definitions are again, okay, they are equivalent, and you can look this up. So maybe the big thing you should remember here, the important thing is that in first order stochastic dominance, we make a very weak assumption. We only assume that people prefer more to less. We even are not interested whether they are risk averse. So if you compare two stochastic prospects, two risky prospects, and they have those distributions here, and they never intersect, then you immediately can say, okay, F is better than X. A person who prefers more to less will actually go for the investment F and not for the investment X. Now, if you observe this here, then you have to be a little bit careful, okay? And you can say, okay, the person will, okay, prefer F, the prospect F to the prospect G, okay? If really this area here, okay, is more than that area, because then actually still, okay, the expected wealth from the F prospect will be bigger than the expected wealth from the G prospect. Then the expected utility or wealth from the F prospect is bigger than the one from the G prospect. That's the first definition of second order stochastic profit. So when you have intersecting curves here for different risky prospects, then you must assume, okay, that people are risk averse. But even risk aversion is naturally quite a natural assumption. Probably 99.9% of people are really risk averse, okay, because the risk lovers, they run in trouble, okay, they may actually make huge losses, and so it's not particularly attractive. Now this applies to insurance demand. You see, insurance, you buy insurance to transform the distribution function of a peril. And people prefer buy insurance if they prefer a new distribution function. So maybe with insurance you don't get rid of all the risks, but you get rid of part of the risk at least. And if that new distribution function you prefer it to the old one, yeah, okay, then you buy insurance. So here I have now a bit more general approach. Insurance just changes you the risks. Okay, changes you the distribution functions of the perils, and it reduces the risks. But maybe it does not remove all the risks. So maybe if insurance really leads to this situation here, that with insurance, okay, then you have the distribution F and not G. Yeah, okay, naturally, then you buy insurance. Now here, if you're risk averse, okay, and insurance produces you the distribution F instead of G, again, you will buy insurance. Now, actuarially fair insurance does not change the mean of the loss distribution, but it reduces the risk. It uses dispersion. So that's mean preserving spread. So a risk-averse person buys fair insurance because fair insurance second order dominates, no insurance. It's exactly what happens here with the mean preserving spread. Actuarially fair insurance does not change the mean of the loss. It's actually fair, but it will reduce the dispersion. And so actually fair insurance dominates non-insurance, and people buy it. So we can make this argument that people buy actually fair insurance just by referring to second order stochastic dominance. You really don't need to know the exact utility function. It's just sufficient to know that people prefer more to less, and that they have a concave utility function. And the exact shape of the utility function you don't need to know. An argument like this I made actually when we discussed the index of the weather index insurance. Now, maybe you look that up again. There I used the concept of second order stochastic dominance. You may go back to that one again. Now, that really, that's all I have to say, okay, on stochastic dominance. As I said, economists try to look for utility functions. They try to model the behavior of people in the market using utility functions. But sometimes maybe that's too tough, okay, to find those utility functions. And now here in insurance and with risk, we still can say something even if we don't know the exact utility function. But we just make some common sense, almost common sense assumptions of the utility functions. In first order stochastic dominance, we just simply assume that people prefer more to less here. And this settles the issue when you have risk-free prospects like that. In second order stochastic dominance, you also assume that people are risk averse. So we have concave utility functions, and that then actually settles the issue when those prospects have here intersecting CDFs, cumulative distribution functions. So and again, you can actually say versus a person, okay, prefers one situation or the one or the other. Now I will provide you in the next lecture, I give you a short example from agriculture economics. This is actually quite used in agriculture economics because naturally farmers face a lot of risks. Okay, what will rain? Okay, and so will a crop really be successful or will the crop fail? And okay, here, okay, you can actually then really say something about the behavior of farmers, how they should behave, even if you don't know the utility function. Okay, that's okay for today, the lecture for today. So thank you.